Now we start with two talks. So the first one will be given by Marli Cantarino, and she'll be talking about competing magnetic excitation and electronic structure in chromium-doped barium iron arsenic insights from RIXS and ARPES. Marli, please.
Thank you. I would like to start to thank you, the organizers, for the opportunity to be here today. And my name is Marli. I'm currently a postdoc at the European Synchrotron. And today I'm going to talk about this that Eric just explained to you. And I would like to do this talk based on the results of my most recent manuscript, which should be available for you tomorrow. And at the same time, I will wrap these scientific results with the full story of my PhD. So it started in 2019. So let's start. So my PhD project was supervised by Fernando, together with Tulio from the Brazilian Synchrotron. So I'm experimentalist, in case you haven't noticed. We have samples from the group from Unicamp, and the title was Electronic Structure and Magnetic Excitations of Magnetic Superconductors. But the title was already a lie, because my samples were not superconducting. So this was the phase diagram. I was interested in chromium and manganese doping of this parent compound. And this parent compound is very famous for having many different routes to achieve the superconductivity. So you can apply pressure, you can substitute in different sites of the lattice to achieve the superconductivity. But these two specific transition metal dopings, they don't give rise to any superconductor dome. And more specifically, I was interested in the low doping region of the phase diagram, where we see the suppression of the antiferromagnetic spin-dense wave transition. And I was curious. This was the initial outline of my project, and I was very curious because when you have whole doping by potassium in the bottom side, you have the highest transition temperature for this kind of materials. So there is not only an electronic compound here, but it's also a magnetic compound, because I'm diluting the iron lattice. And when you do magnetic doping on the iron side, for example, for europium, is it still possible to have a superconductor dome in this case? So there is something specific about these two dopings that I wanted to investigate. And to do that, first I will start with theory. Not first, but this was one of the scenarios I was trying to understand what happened to this kind of materials. And as far as we understood at the time, the superconductivity in the iron arsenides is formed by the combination of electron-electron repulsion and boosted by spin fluctuations. So you have to have the right kind of magnetism underlying interactions or fluctuations to help to promote the superconductivity. And then when you dope, you can understand this dope, the transition of the magnetic, the suppression of the magnetic transition in different ways. There is different scenarios. So one of the scenarios, you see these antiferromagnetic excitations is scattered by the Niel excitations introduced by the dopants. So you have a competition of different natures of excitations in this case. And in these excitations, they will be the ingredient that suppress the S plus minus superconductivity in these materials. Another way to see this is if you have the magnetic impurities having a collective behavior, this behavior could decrease the electronic coherence because of the electronic interaction with this magnetic impurity. And this will suppress the transition temperature by this pair breaking mechanism. Of course, we have the specialists here in the audience, so if you have specific questions, you can ask them also. But then, after I started the project, I already had some results. There was the scenario of Hans metals, because these kind of materials, they are known as Hans metals, which is basically a metal with localization. And the localization, it comes from the strong Hans coupling. So this creates these localized moments which are orbital dependent. So this can only happen in a multi-orbital system, which is the case of iron arsenides. So when the iron arsenides start to be studied, many people start to develop minimal models based on the cuprates, but the cuprates, they are single bands. So the thing evolved a little bit, and now the theory is very different from the cuprates. But it's important to notice that in Hand metals, the correlation will be orbital selective. So there will be different renormalization for different orbitals. And it's expected that when you hold dope these materials, you bring the system closer to a mod state. So you should be enhancing the localization. And so we understand this orbital selective physics as different energy scales for the charge screening and the spin screening. So this could also bring some insight about the dual nature of itinerant and localized physics in these kind of materials. And this also correlates with the nematic order. So from this understanding that I had at the time, I had two techniques on my project. One was ARPES, where we can directly probe the electronic structure, and the other was RIXS. RIXS is the technique I'm working more now. And with RIXS, we are capable of see the elastic excitation. So in case you are not familiar with RIXS, RIXS is a resonant inelastic X-ray scattering, meaning we do this spectroscopy with the same incident energy as the X-ray absorption spectroscopy. So we probe the edge of a specific element. It's inelastic, so we have this energy loss detection. Is in a similar way to inelastic neutron scattering. But then it's X-ray, it's not neutron. So because of that, we have the particularities of light-matter interaction and also different penetration dips, but it also allows us to do this technique in small samples, in small volumes and thin films, which is not possible for inelastic neutron scattering. And it's a scattering technique because we use the geometry of the experiment to probe the momentum transfer to the system. So it's also momentum resolved technique. And with RIXS, we are able to see different excitations because of the energy transfer between the incident photon and the detected photons. As for example, phonons, plasma, orbital excitations, all of these, but I'm more interested in the magnetic excitations for these materials. And every different excitation that we can measure with this technique will have a specific energy scale. So in the case of magnons, they are very low in the energy scale, which for inelastic neutron scattering is not a problem because the resolution is usually very good, but for RIXS it can be a problem because our resolution is not as good. So we really needed a very good resolution to actually probe this when we start to dope the material. So this is about the technique. Now there was a few challenges because I had a thesis, it started in 2019, to do synchrotron experiments, but then it came the pandemics. So I was a little bit stuck, let's say, but the solution, it came from in the form of internship. So I went to Switzerland and to do ARPES, to learn ARPES in a university lab. So I was there visiting student in the group of Claude Monet, and they had this nice detector here, is the spherical analyzer, is the ARPES detector, and I learned a lot with them, and together, the three of us, Bjorn, Claude, and me, Bjorn was a PhD at the time, we went to the blobbing line 2021 to do the first experiment of my project. So, I mean, the first is a spectroscopy experiment of my project. So I was already in the third year of my PhD doing this kind of experiment, but luckily we had a lot of expertise with the same detector because they have exactly the same in the beam line there. So we had a very profitable beam time. In 6 days, we measured 7 samples in 2 different temperatures for most of them. So it was very good, and I got basically all the results of my thesis in that 1 week. And so I talk about manganese and chromium. The paper I want to discuss more is the chromium one, but just to contextualize, the first paper that I published was about the manganese, ARPES results, and what we saw for the manganese is that the manganese does not directly perturb the iron electronic state. So when we see the electronic structure, this is a cartoon with the biggest effects that we see at the paramagnetic temperature. What we see is that the whole pocket size are almost unchanged. The only difference that we could actually see was the where is my pointer? Yeah. The electron pocket was getting a bit shrinked in one direction, so not isotropically, and all the bands they are getting broader. But this is some incoherence because of the doping of the system. And another thing that we saw is that when you go to the 8.5% manganese doping, you still have the splitting between the GXZ and GYZ bands, which is characteristic of the orthorhombic distortion and the nematic splitting of these orbitals. So in this sense, there was no much difference when we dope between the parent compound and the 8.5% manganese sample. And the biggest difference was in the incoherence and the width of the spectral function. But then my supervisor had started already investigating these materials just before I started my PhD, and he had this paper. It's RIXS results on the manganese sample, and what the main results of this paper was that the manganese substitution was causing this anisotropic magnum dispersion dumping. So this is shown here. So when you look at the pi-pi direction, the excitations, they have more or less the same energy with doping. But when you look at the pi-0 direction, the excitations, they are having a smaller energy with doping. So the pi-0 direction is the iron-iron direction. So the dilution with manganese was making the iron-iron specific iron derived excitation dumped. And RIXS, as I said, is a resonant technique. So I'm only looking at the magnetism derived from the iron. So there was some other results that we studied at the time. There was this paper from 2013, and they use a Moon spring relaxation, nuclear magnetic resonance, and neutron scattering data to show, to claim that there was this drift regime close to this. Okay, this one is better. Okay, thanks. Maybe I don't get mixed up. So, yes, neutron scattering data to probe the magnetism of this doping phase diagram. And what they see is like there is this spin glass, cluster glass, and supposedly a drift regime close to the quantum critical point here. And they say that this spin glass is formed by the localized magnetic moments randomly embedded into a metal. So they form their own order, not interfering so much with the iron order. And this also aligns with the fact that there is no directly doping of the iron bands. And this will also explain the suppression of the antiferromagnetic transition temperature. But then, when I look in overall for my manganese results, as I publish it, what we see is like the nesting scenario does not explain the suppression of the antiferromagnetic transition, because we see the same splitting, the things are not changing in the electronic structure point of view. And the absence of high temperature superconductivity in this phase is interpreted in terms of this magnetic impurity scattering the magnetic excitations, which should be important for the superconductivity. And then now I will turn to the chromium case. What we see for chromium is already different. We have seen that the Fermi surface is actually hole doped, so the hole pockets are getting bigger. And this was reproduced by DFT plus DMFT. So this is a sign that the system is in fact correlated. And we see that the band splitting that we saw on the parent compound and on the manganese compound is not there anymore. And the bands, this band specifically that goes to the hole pocket is much more flatter. So in this case, what we saw is that there is this orbital specific localization and flatter band that aligns to a picture where the effective holy doping is bringing the system towards a more localized state. So we did also the spectral analysis to get some more quantitative insights from the ARPES results. And what we saw is like there is fractional scaling of the imaginary part of the self-energy. And this is a signature of a Hans metal. And then we saw similar disorder effects as the manganese, so the bands getting broader. But we don't have any evidence for any from other works of size of cluster order or impurity cooperative behavior in this case. So the chromium having the same spin as the iron, they're effectively perturbing the iron electronic states. So in 2023, I got a beam time to do RIXS finally, which was in my original project in 2019. And one more before I submitted my thesis, I went to Diamond in England to do these measurements. This was 2 months before my defense, so it was quite hushed. So this is now is the results of the manuscript, which you could probably read tomorrow. And what we see is that for the parent compound, as I mentioned, we have this stripe type order. And then with RIXS, we can probe this blue circle here. So we have access in reciprocal space to the ordered Brillouin zone. And when you look at the results of the parent compound, what we see is that there is this, this is the magnum peak after we subtract some other contributions at higher energy loss. And you see the dispersion of the peak as a function of momentum, and different peak shapes in different directions of the reciprocal space. And when you look at the doped sample, what we see is that the 3.5% chromium sample is very similar to the parent compound, doesn't change that much. But when you go to 8.5% chromium sample, the magnum is much more damped and lower in energy. So it's almost as a shoulder of the elastic contribution. So to do a more quantitative analysis on this, we can do these fittings. RIXS fittings can be very different from time to time. You have to convince yourself and after convince the referees. But basically, we have the elastic line. There is always a present component in this kind of experiment. Phonon contributions, which are normally low in energies. And because we had very good resolution, we could see the magnum very clear. But I also add this supposedly B magnum contribution, because if I only fit a single magnum here, I cannot reproduce the very sharp and at the same time asymmetric shape of this contribution. So you don't expect the magnum to be sharp and asymmetric at the same time. So I added another contribution here. And this is not necessary for all the fittings. Sometimes I don't need this. I have a very good fitting without adding this. But what we see finally is that as I mentioned, when you look at the propagation frequency, the maximum of the peak is very similar between the parent compound and the 3.5% chromium sample. But when you have the 8.5, you start to have this dumping. And when you translate this into the fitting model, so I have a bare frequency and a dump factor, I see that the dumping is much bigger for the 8.5% chromium sample, but the bare frequency is very constant. And then I compare this frequency with linear spin wave fittings from inelastic neutral scattering data, and it's very similar. So we have results. We don't understand everything, so we ask help for the theoreticians. Then Eric here and his postdoc, they developed this model. Maybe he can explain better than me, but I will try to explain. It's a Heisenberg model on a square lattice with almost 2D model, so I have a weak out-of-the-plane coupling. And it's on a limit, it will be an L order, which is the case of the barium chromium 2 arsenic 2, and on the other limit will be a stripe order. And to implement this order on the system, the chromium substitution will change the J2, so only the second neighbors will be changed. And in case I have an iron-iron coupling, the J2 will be 2, especially because in RIXS we only probe the iron contribution. If I have a chromium-chromium, I don't see it. If I have an iron-chromium, I see half of the exchange parameter. And with this simple model, on top of that, there is a numerical implementation with Monte Carlo. So there is an initial spin configuration, and then there is this updates of the initial configuration, and different disorder will have different orders, degrees of doping to reproduce the actually impurities and the chromium doping in the material. And there is the semi-classical molecular dynamics, so the time evolution of spins with these equations of motion with time evolution. And at the end, the Fourier transform to get from this model the dynamical spin structure factor. So this will be the structure factor that we'll be comparing with the experiments. So this is the result as a function of doping. I have 0, 5, 10, and 15% here on this picture. And what we see is that the excitations, they're getting larger, so we actually see the dumping in the theory. But there is also this transfer of a spectral weight towards the x and y points. So the propagation of the excitation is not the same anymore on the reciprocal space. Yeah, yeah. Yes, yes. So the x and y are the order moment of the stripe order, but yes. Um, but then I have different lattices because of yes. But this x, y, yes, yes, yes. So from this, I can compare with the experiments. So I also have the 8.5% here. I have the same color scale, which helps a lot. And then I can have the cuts at the y bar point, which is the maximum of moment I can reach on my experiment, going to the pi0 direction here. And as a function of doping, we see this bigger width of the excitation, and also the transfer of the spectral wave towards smaller energies. So this is effectively the same effect as the dumping on the experimental data. This is the experimental data, but the fitted function from the experimental data. That's why it looks so nice. So I see also from 0 to 8.5 the softening and the dumping. Here the softening is not so well reproduced by the calculations, but the dumping is very well reproduced. And then we think of these differences as the charge doping also contributing to the softening somehow. So looking at the chromium from this perspective point of view, we think that the main effect suppressing the atom magnetic order temperature is the introduction of competing magnetic interactions. And this is because of the comparison of the RIXS with the theory. And trying to understand everything that we saw for this phase diagram, the absence of the high temperature superconductivity should be because of the magnetic scattering and suppression of the itinerant spin fluctuation, which would promote the superconductivity. So now that I talk too fast and too much, the conclusion and outlook is that the Fermi surface changes with chromium manganese, they are different, and they are unrelated to the transition temperature. So irregardless of what is happening to the electronic structure, we have the same, almost the same phase diagram to the low doping regions. Different electronic and magnetic effects can suppress the formation of superconductivity. So we have different behaviors and suppression for the both samples, for the both phase diagrams. And then from this, I try to speculate a little bit, because here on this work, I don't have considerations on bond lengths, angles, or chemical pressure, nothing of this sort. And we know this is important. The iron arsenide distance, for example, is very important. So I don't go to this side of the study, but I conclude that for these materials, they require the right combination of underlying magnetic fluctuations and electronic itinerant states to allow not only the necessary conditions, but some of the conditions maybe. And as a outgoing message also, local disorder is an unexplored ingredient in enhanced metals. We don't know exactly, as far as I know, what is the importance of disorder in this case. And with that, I would like to thank you for your attention.
Thanks, Marli, for this nice talk. Questions?
So I remember that, I think it was you, Rob, it measured that in the manganese doping, after sufficient manganese doping, the ground state changes to a double Q phase, which you have the 2 pi 0 and 0 pi, but no orthorhombic distortion. So I don't remember exactly what doping was that, but do you see this change of magnetic state as you start increasing the doping, the manganese doping?
So this that you're talking about is after the quantum critical point. So if you look at this phase diagram that they did here, this behavior would be after this quantum critical point around 15%. So we never went to that region because we are interested to always have the same ground state.
Okay.
So I limited the study to this part of the phase diagram.
So in your experiments, you see a transfer of spectral weight from the 2 magnum peak to lower energies. And in the simulations, you mentioned the transfer of spectral weight between X and Y points. Are these two phenomena related?
No, because when you look at the color maps, what you see here is like the spectral wave is transferred to lower energies. So this is what I call damping. So the peaks are getting broader. So this is one effect, and then on top of this effect, there is also the other effect of bringing the spectral wave to another Q point. So they are not the same thing, but they're also both of them happen with the doping. Maybe they are related. I don't know.
My question is perhaps for discussion later. It's not so easy, but you have an insight of the key difference between these families and those doped with cobalt? Why a superconductivity is there and not here, or I don't know. It's not. I don't know. If it's easy to you have some insight or some feeling about the key difference between these two different doping, because the other one has also magnetic doping and superconductivity emerged. So
yes.
but perhaps we can discuss later.
Yeah.
I don't know.
It's interesting that you ask, because from the point of view of ARPES, I know that there are studies on the potassium and cobalt, for example, and they show the whole doping, so effective changes on the electronic structure when you dope. So cobalt and potassium, which are whole dope and electron doped parts of the phase diagram, give rise to superconductivity, they show effective changes on the electronic structure. So they will be similar to the case of chromo. But this is not the only necessary gradient, because something else must be happening to suppress the superconductivity. And then in that case, for example, this splitting of the nematic size that I showed to you as a function of doping, I never saw any other study doing this to the doped samples. I saw studies doing this to the iron selenium, to the parent compound, but not for the doped samples. So I don't know, for example, what happens to the case of potassium and cobalt. So I don't know, many ingredients. We can discuss more later.
Mentioned that the doping doesn't change the value of J1, just of J2. Is there a simple way? Why is that? Simple way to understand this?
As far as I understand, maybe Eric can explain better. Because we are in the low doping region of the phase diagram, you don't have enough dilution to actually change so much the first neighbors in overall. But I'm not sure. Maybe Eric can answer you.
If I put this order on J1, does it takes account the spectral weight transfer? Do you know it?
Did you hear the question?
Yes. I'll discuss later.
Okay.
So I think not, I think the answer is no, but I
Okay.
can talk later. More questions? So just to remind you, Marli is going to be here just today, so
Yes.
we're going to talk to her.
Yes.
So please do it today.
Tomorrow
so
I'm going back to France.
Okay, so let's thank her again. Thank you.